This continues our presentation for Chapter 13, Fundamental Equilibrium Concepts. In this particular video, we're continuing with Section 13.4 and working on Sample Problem 3 from the lecture handouts. Problem 3 gives an equilibrium constant value, Kc, for the reaction of the formation of ammonia gas from nitrogen and hydrogen gas. Kc has the value of 5.97 times 10 to the minus 2 at 500 degrees Celsius. If 1 mole of nitrogen gas and 1 mole of hydrogen gas are heated to 500 degrees Celsius in a flask of volume 10 liters, together with a catalyst, calculate the percentage of nitrogen converted to ammonia. So again, we want to start by writing the equation for our balanced chemical reaction. And setting up our ice table. Notice that we're given Kc again in this equation. Even though the reactants and products are in the gas phase, we still want to use concentrations because we're given a Kc. So our value of 5.97 times 10 to the minus 2 is going to be equal to the concentration of NH3 squared divided by the concentration of nitrogen divided by the concentration of hydrogen raised to the third power because of the 3 coefficient. So we're told that we have 1 mole of nitrogen gas in a 10-liter flask. What's the initial concentration of nitrogen then? Remember that molarity is moles over volume, so we have 1 mole of nitrogen in 10 liters gives us 0.1 molar nitrogen. We also have 1 mole of hydrogen in the same volume, so we're starting with 0.1 molar hydrogen gas as well. We'll assume that we're starting with 0 of the ammonia gas. Again, since we're starting with only reactants in this situation, the reaction will have to proceed in the forward direction to reach equilibrium. So we'll use minus x as our change for the nitrogen, minus 3x for our change for the hydrogen, and plus 2x for our change for the ammonia. The equilibrium row is the sum of the initial plus the change. Plugging these values into our Kc expression, we see that we have our work cut out for us to solve this equation for x. We're going to end up with x into the third power. We can't use the quadratic formula to help us here. There are other methods to solve this, but a good thing to do here is to make some reasonable assumptions that will help the math be easier. One thing we notice about this equation is that the value of K is small. What does that mean chemically? That means that at equilibrium, we expect mostly reactants and not so much products. Since we're starting with reactants in the system and no products, we expect the amount of change that happens to be relatively small. So let's try making the assumption that x is small. Again, I'm going to start a new slide so that we can have more room. So we have our expression again, Kc So if we assume x is small, what does that do for us? Well, we can't neglect x in products up here, but what we're going to try is to neglect the x values in any sums or differences. So if we assume that x is small relative to 0.1, and also that 3x is small relative to 0.1, we can rewrite this Notice that's greatly simplified the math. Multiplying through, we get 4x squared is equal to 5.97 times 10 to the minus 6. X squared should be, and again I'm using approximately here because we've made an assumption. And I'll go ahead and take that all the way down to our approximate value for x of 1.22 times 10 to the minus 3. We now need to check our assumption. What do we mean by that? We said x should be small relative to 0.1. How small is it? Let's figure out what percentage of what percentage of 0.1 x actually is. So we're going to calculate x over 0.1 and express it as a percentage. So x is about 1% of 0.1. We're going to use a rule that as long as our assumption agrees within 5%, in other words, x is less than 5% of the value that we're neglecting it from, that we can make this assumption. We should also check to see whether 3x is in fact small relative to 0.1, because that's another assumption that we made. And this time we get 3.7%, which is also still less than 5%. So this means that our assumption that we can neglect the x in the sums and differences in the k expression is a reasonable assumption. In other words, if we went back and plugged in our value of x into these terms in the kc expression, it wouldn't change things very much. So let's continue. We have solved for a value of x of 1.22 times 10 to the minus 3. So now we need to plug that x back into our expressions for the equilibrium concentrations of nitrogen, hydrogen, and ammonia. So for the concentration of nitrogen, our equilibrium value was 0.1 minus x. Plugging x into that gives 0.099 molar, which we see is very close to 0.1 because the change was actually small. The equilibrium concentration of hydrogen gas was 0.1 minus 3x, or 0.096 molar. And the equilibrium concentration of the ammonia gas was 2x, or 0.0024 molar. So we now have the equilibrium concentrations of the reactants and the products. But what did the question actually ask for? It asked for the percentage of nitrogen converted to ammonia. How would we express that mathematically? We want to compare the change for nitrogen to the original amount of nitrogen. The change in the amount of nitrogen was actually X, and our original concentration of nitrogen was 0.1 molar. And we're going to go ahead and express this as a percentage. So the percent nitrogen that was converted is actually 1.2%. Let's go ahead and look at question B. Again, we have the same reaction and the same equilibrium constant. This time we're changing the volume. Instead of 10 liters, we have 5 liters. So again, we'll start with our balanced chemical equation. Set up our ice table and our equilibrium expression. So we're still starting with 1 mole of nitrogen gas, but this time in a volume of 5 liters. This gives an initial concentration of 0.2 molar. And we have the same for the hydrogen gas. We'll start with 0 of the ammonia gas. For the change row, we have minus x for the nitrogen, minus 3x for the hydrogen, and plus 2x for the ammonia. Again, because we know since there was no products initially, the reaction must shift forward to produce at least some products at equilibrium. To get the equilibrium row, we combine the initial and the change row. Then we plug these equilibrium expressions into our Kc, which remember had a value of 5.97 times 10 to the minus 2. Again, we see this power of 3 in our equation, which is going to make the math difficult. But we can use the same assumption that we used in part A. At least we can try it. So let's try assuming that x is small. Why can we assume x is small? Well, we have an equilibrium constant, which is much less than 1. Again, this means that this is a reactant-favored process. So at equilibrium, we expect there to be mostly reactants and not too many products. Since we're starting with mostly reactants, the change or the shift shouldn't be very large. In other words, x is small. Where can we neglect x's? Again, we can't neglect x in any products because then it would just take that term to 0 and we can't do that. But anytime we have a sum or a difference, we can try assuming that the value of x is too small to be important relative to the other number in the term. So if we do that, we have 5.97 times 10 to the minus 2 is 4x squared over 0.2 times 0.2 to the third power. Again, that's going to make things a lot easier. Rearranging and solving this for x, we have x is equal to 4.9 times 10 to the minus 3. So is x small? We need to check our assumptions. I'm going to go ahead and switch to a clean slide to give it some more space. So right now we're working with the idea that x is 4.9 times 10 to the minus 3. And we had the expression previously that our kc was 2x squared over 0.2 minus x and 0.2 minus 3x cubed. So we need to check to see whether or not x was small relative to 0.2 or whether 3x was small relative to 0.2. Obviously, this is the one that's going to cause the most problem if there's a problem. So let's check to see what percentage 3x is of 0.2. And this ends up to be about 7%. Okay, so we had a 5% rule. 7%, unfortunately, is not less than 5%. So, does that mean we have to start all over? No. This value of x is still a reasonable assumption or starting point for a value of x. Our x should be relatively close to that. What we're going to do now to get a better value of x is something called iteration. We're going to go back to our kc expression and solve it for this x. So we have 4x squared over 0.2 minus x times 0.2 minus 3x should be equal to 5.97 times 10 to the minus 2. 4x squared I'm going to bring the terms in the denominator over to the other side. Divide by 4 and take the square root to solve for x. Okay, so now what? What we want to do is use our value of x here, plug it in to any sums or difference on the right side of the equation to get what we're going to call a new value or a better estimate of x. When we plug in 4.9 times 10 to the minus 3 into these terms on the right side of the equation, we get 4.3 times 10 to the minus 3 as our new value of x. Notice that it's not the same as our original value of x, but it's not that different either. What we want to do is keep doing this until it converges. Converges means that we get the same value out that we put in. So we're going to go ahead and put in, sorry, that's not working, the 4.3 times 10 to the minus 3 now in for our terms on the right side. Do all that math on our calculator, and we get 4.4 times 10 to the minus 3. Try this on your calculator and make sure you're getting the same numbers I am. Okay, so our, in that sense, third value of x is now very close to our last value of x, but not quite. So we do this one more time. And this time we actually get out the exact same value that we put in. And we say that our solution has converged. This means that at least two significant figures, this is a good value for x. So our value of x is 4.4 times 10 to the minus 3. But again, that's not really answering the question. We need to go back and plug that in to our equilibrium concentrations of nitrogen, hydrogen, and ammonia. So for the nitrogen, we had 0.2 minus x, or 0.196 molar. For the equilibrium concentration of hydrogen, we had 0.2 minus 3x, is 0.187 molar. And our equilibrium concentration of ammonia was 2x, or 0.009 molar if we assume that we're doing all of these to the thousandths place. What percentage of nitrogen was converted? So how much nitrogen did we actually lose? We lost X amount of nitrogen compared to our initial concentration of 0.2. Expressing this as a percentage, gives us 2.2%.